everyone for making the time today. This will be the second workshop out of 4 we are giving in a period of 2 months. Some of you attended a couple of weeks ago geophysics for geologists, but for those that missed it, a recording of the presentation is available upon request, so please feel free to send me an email. Our topic for today is an introduction to DCIP. We'll also talk a bit about deep IP imaging as well. The presenter today will be Rob Gordon, geophysicist with more than 40 years of experience. I'm sure many of you have met Rob in the past. He's been the face of Quantic for a while. Also today we have Jeff Warren as a panelist. He's part of our intergroup and will be available during the Q&A session. Finally, I should mention that a copy of the presentation will be available, so don't need to make notes. So now I'm going to pass this over to Rob. I'm gonna turn on my camera here and I'll be back later.
Yikes. Well, thanks, Christian. And thanks everybody for taking the time out to join us today for this lively presentation on DCIP. Hopefully it'll be at the right level. IP can be a complex topic, and but I think the principles of it are something that most geoscientists should make the effort to understand. So hopefully we're hitting at the right level. I'm just going to turn my own camera off as it's a little bit of a distraction to me, and barrel all in. Just before we get started, I'll give you just a very high-level overview of Quantic. Many of you might be familiar with us, some of you aren't. We've been around since 1986, and this is sort of a timeline of various things that we've done over the years with regards to growth, etc. On the left, we expanded down into South America, where we still operate several offices and do a lot of work. In and around 2000 was a very busy time for us with helping launch Mira Geoscience and bringing the importance of physical property logging into the industry. And at the top here, you see DAS. We were the first group to commercialize distributed acquisition technology, following on the introduction of that by MIM DAS over in Australia with the Titan. And then to the right, we have developed 3D DAS technology, and more recently, you've probably noticed we did a little bit of rebranding, and we're now focused on providing flexible, deep imaging technology, including Spartan MT and our Orion. In addition to our principal technologies, Titan is really referring to 2D distributed array-based technology. Orion is our 3D services, and Spartan is related to our MT, resistivity, deep imaging resistivity technology. And then we have a fairly substantial interpretation group based in Toronto in South America that does everything from survey design, planning, and interpretation of data. And of course, we do a myriad of other geophysical surveys as well. For those of you who haven't worked yet with us, Quantic focuses on conducting surveys in a safe manner, and we provide reliable services. We have a track record of delivering results on time and on budget. Our flagship technologies are amongst the most advanced available to provide accurate information about the subsurface. I'll leave that behind and we'll get into the presentation today. This is an overview of what we'll be talking about. So we'll talk a little bit about the IP effect, history and developments through time. I'll touch on that. Applications. Important things about DCIP surveying are data acquisition, and subsequent to that is processing and inversion. At the end of the presentation, we'll talk a little bit about depth considerations and touch on the distributed technology Titan. So IP, a lot of people will ask for an IP survey. Well, this is just sort of for clarification out there. It's an IP survey should really be called a DCIP survey. And the reason for that is this survey provides two very key physical properties that are measured. And so the DC is representative of direct current, resistivity, and IP. So that's a little bit of a backdrop. And then the other thing that we mention a lot of, and we sort of take it for granted when we're talking to many geologists and other geoscientists, we'll talk about dipoles. And oftentimes a lot of people don't really know what that is. Well, essentially it's going to be 2 points of measure. An electric dipole deals with the separation of a positive and negative charges found in any electromagnetic system. And so basically, when we talk about a dipole, we're going to, hook a wire between these two things and measure that dipole out in the field. So, what is the IP effect? Basically, what we're doing, if you look, hopefully this isn't too complicated, but on the left we have a square box. You see that it says on time, off time. What we're going to do is, in this simple drawing here, is we're going to turn on current, and it could be, you're turning on a light bulb, and we'll leave it on for a little while, and then we're going to turn it off. And essentially that's the current waveform that we're going to put into the ground. We're going to turn something on, we're going to turn it off. And the neat thing about IP is when you go and measure a dipole, what happens is when you turn that current on, when you measure the voltage somewhere else, there's a noticeable increase in voltage from a steady state. So you see the curve kind of goes up here. And then when we turn it off, it drops down, but it doesn't completely go away right off the bat. It kind of takes its time to generally fade away. And so if you went out to the garage and you turned on the light and turned it off, it goes on and off right away. Well, this effect here that we're experiencing is essentially the IP effect. We're inducing a charge in the ground, and then the ground is that charge dissipates over time. Essentially, that's the IP effect in what we refer to the time domain. In the frequency domain, it's the same. And when we talk about frequency domain, all that's happening differently is instead of using a DC current where you turn it on and you turn it off, we're actually using an AC current, so it's on all the time and it's oscillating. And what's noticed in the voltage responses is a shift, and that is in fact the IP effect. So it can be measured in two different ways. And just going back to the dipole and what's happening in the ground. So basically, the principle of all this is based on a fairly simple electric circuit. And the circuit is a sort of a loop that, if you look at the little diagram here in the middle, the current I is the current source. The red dots are where we're going to measure the potential, and the ground is the resistance. So there's a very simple relationship that's V equals IR, which is voltage equals current times resistance. And that's the principle that's being used here. So we're going to introduce a current in the ground, we're going to measure a voltage, and we're going to calculate the R based on this. And you can imagine if you move this voltage away off to the right someplace, the current has to travel further through the ground, and maybe it's obstructed by various things. So that's the resistance that's happening. And so if you look over to the right here, if you have something that's not chargeable at all, the voltage that you're measuring with regards to the chargeability side of things is just going to go. You'll measure a voltage and you won't see a voltage. So if it's not chargeable, but if it is chargeable, you're going to see this effect on the voltage that we talked about earlier. And basically, what's happening is on the DC resistivity side, it's quite simple. It's just that circuit that we're talking about. On the chargeability side, what's happening is there's actual charge that builds up on various surfaces. And so when the little guy here on the lower right, when he puts current in the ground, the various things that are in the ground cause the charge to build up on the various surfaces, and that's the phenomena that we're going to measure. And the reason I mentioned that it's fairly complex is that what's in the ground isn't always a uniform material. So this buildup of charge happens on these various surfaces with respect to surface area and such. And so the type of material that's in the ground and at the microscopic level, this effect is happening. And so as you build out sort of a bulk of material of, could it be clay or could it be sandstone or whatever that microscopic effect that's happening down at that level kind of gets translated into, the lower right, the net charge that's happening in the ground underneath a specific area. So once we've sort of understood a little bit about what's happening, and then we go to measure it, eventually we're going to present these readings that we get in certain units. And these are for time domain and frequency domain, DC resistivity. It's common across the industry. It's ohm meters. And you can see the left-hand scale bar here is a typical resistivity scale bar in ohm meters. 10 shown in purple is low. So that low resistivity is means that things tend to be more, the low resistivity is high conductivity. So it's more conductive materials are down in the purples, and the blues are shown as high resistivity. This can, depending on the environment, can be anywhere from 10,000 to 100,000, depending on the different rocks that you might encounter. Chargeability, depending on which style of IP that's being done, frequency or time domain, can be in millivolts per volt or milliseconds and or millirads or percent frequency effect. We commonly use millirads in our work. As far as history and development go, we put this slide together just to capture some of the different things that happened. But essentially, this effect was noticed way back at the turn of the century by a fellow named Schlumberger, who went on to have a very storied career in geophysics and the oil industry. And then later, probably the next most significant thing was in the late 40s. It was really demonstrated that the method was something that was reliable in terms of consistently getting similar readings over different things. The early 50s, Newmont and Anaconda at the time were spending a lot of time studying the various different, whether it's frequency or time domain. And eventually the time domain method became sort of the more predominant method going forward, but the frequency domain still exists in various forms. In the 90s, there was sort of probably the first 3D type of system came along, which was sort of a switching system. So there's lots of cables and wires out, and arguably a little bit of ahead of its time, because the data that it collected, there wasn't really a lot that could be done with it at the time. It wasn't until sort of the late 90s that 2D inversions started coming out, and we'll talk a little bit about inversions later. And then in the late 90s and 2000, a fellow named John Kingman, well respected in the IP world, developed the first DAS system, and I've referred to that a couple of times. And the first, arguably, was the MIM-DAS system out of Australia. And he subsequently came to North America and spent several years developing up the next generation DAS system, which was the Titan system. And this technology had a bunch of sort of technical names here that I talk about: current monitoring, full waveform, multi-parameter, that helped really drive out better signal to noise, and the ability to sense very small changes in the subsurface. So that was a big step. And then since then, it's mostly been advancements in the processing and inversion technologies. So UBC and LOC in the early 2000s started with 3D inversion of IP. And then in the mid 2010, it was the first 3D IP surveys. 3D DAS systems were coming online. And then more recently, it's sort of taking those surveys and systems and trying to be more efficient and making them more flexible, so that more people can entertain doing 3D surveys. In the oil industry, when they invented 3D seismic, there was just a mass stampede of people into the 3D seismic world, and the utilization of 2D went down drastically. We haven't seen the same thing in the mining industry, more or less, because the electrical 3D measurements are very complex, and the geologies in related to mining application hard rock is much more complex than more simple stratigraphies that we see in the oil sector. As far as applications go for this method, and I just put these scale bars back on this slide, actually to add a little color, but several things that we're going to be able to do with IP surveys. We're going to be able to look for conductors. Key for a variety of things are actually looking for resistors. We can detect massive sulfides with this method. And what's really neat, and I talked a little bit about it earlier, is disseminated sulfides. So that whole concept of charge building up on surfaces. Well, when you have disseminate sulfides scattered in your matrix of rock, charge is able to build up on these little particles when you charge up the ground. And so this is a sort of a key feature about the IP method is looking for disseminated sulfides. And so taking just these top 4 points, and then reaching towards how you're using those pieces of information to tie in with your local geology, your lithology, features that are in conductors, and the myriad of things in between. And it's really the exercise is trying to figure out how the response of any given survey relates to your own situations, because everyone's are different. And the segue there to this slide is that, you know, it's really important if you're working a property, especially if you're working it for a number of years and you're trying different geophysical methods to help vector towards, you know, better drilling or a discovery, is trying to get a handle on what actually the rocks are. It's one thing to say, oh, I want to run an IP survey. You go out and you run an IP survey, it's going to provide you know, purple things and light blue things in resistivity, and the same in chargeability. And you're going to either be frustrated if you drill anomalies and don't hit anything. It's sort of a favorite expression of many geologists over the years, is saying, well, that didn't work, when they've drilled some feature and it wasn't a mine or whatever. And the issue really is, well, let's try and figure out what it was so that we can use the rest of the data set to vector towards the features that are in fact the useful targets. Oftentimes these ore bodies, significant ore bodies, are found on the inflection, the gradients of both resistivity and chargeability features, or they're found below you know, disseminated zones that are barren, have the juicy stuff next to them because things have been zoned or whatever. So this is just really a reminder of if you're working in an area, it's definitely worthwhile to put that extra effort into, you know, look at your bad rocks and your good rocks and try and understand what their resistivity signatures are. And that goes similarly for chargeability. And there's, you know, we have a little kit, a lab kit that does, you know, core samples and that sort of thing. They're not that expensive, and arguably, if you're working with a lot of IP data, or people are considering IP data, it's either worth it to figure out how to make some of these measurements yourself, or outsource them just to get a handle. You don't have to do all the rocks, but certainly the nature of geology, it's complex and ever changing, and rarely do rocks fall in single categories, as the last slide said. These resistivities are over quite large ranges, and so it's more or less trying to get a handle on where things are sitting versus the ideal exact number. So there's a variety of ways that we can go and measure these voltages and inject current into the ground. These are several survey layouts that are common in the industry. I won't go into the details of exactly how they're done, but you can see on the right, it says dipole sources inject current less deeply, and essentially, so a dipole survey, for instance, is like the picture on the right, and so your current is going into the ground and having its impact as per the yellow lines on the right hand drawing, and the left hand drawing is, you see there's only one pole there, the other one's farther away, so that's probably either the pole or the pole dipole survey, and you can see that the current lines that are going into the subsurface are deeper. They're just impacting the ground to a deeper level, or they're penetrating is the word. And I show a picture a little bit later on that. So collecting the data in the field for standard IP surveys, usually there's an operator, a transmitter operator who's dealing with the current. There's a degree of safety that has to be involved. A number of helpers help move things along, and usually the operator is coordinating things. This shows, a fellow with a small IP receiver. Wires are stretched out down the line towards those dipoles. So for each of those dipoles that we're going to measure out there, and we'll talk about that shortly, there's going to be a couple wires that go off down the line, and you can sort of see there's quite a clump of wires in the top middle slide here, and it generally involves guys roaming around laying out wire and making these measurements. It's really important. Some things that I actually don't talk about here really, will just now, is making the connection with the ground. In certain areas like the desert pictured down below, and even the rocks on the right, it's very difficult sometimes to get the current into the ground. In some cases in the Atacama Desert, it's about digging a pit with a backhoe and lining the pit with tin foil and putting in saltwater solutions and that sort of thing. Other places where it's difficult sometimes to get good measurements are, on the outcrops of northern Ontario. You can't actually put a rod into a hard rock, so you have to get someplace where you can actually get the current into the ground and or be able to make a measurement. Frozen ground too can also be a challenge, like in northern Saskatchewan. But experienced operators usually have all the variety of tricks in order to ensure that they're getting good data signal. A quick survey example here, just showing it's the Allura ore body, and I borrowed some of this material, just giving a nod to UBC and a couple other websites I've noted in the slide presentation, where you can find this type of information going forward, if you want to refer back to it. But in this, we have they have the geology here, and also noted resistivity. So the mineralization has got a very low resistivity, so it's very conductive. And then there's a Gossan and host rocks and overburden. And just the next series of slides just give you a sense of what we're doing in an IP survey. So we're going to be injecting at one location, in this particular case, and for this type of survey, you could do a gradient survey where you put current in, like the blue, and then you're going to measure the potentials and the across the red, and you could move that red back and forth in here to get more detail, for instance. And what's going to happen? Well, the current's going to go into the ground, and the thing to notice is that, you know, if you put current through a wire, that's how you get, you know, your lawnmower going or your lights on and that sort of thing. So current likes to go through conductive materials like wire, and they like to avoid resistive material. And so that's part of this whole principle, is we're going to be injecting current, and you see how the lines have formed around. So that's sort of the field is shaping up around these various bodies. So they're avoiding the resistors and they're channeling through conductors. And then when we start turning on and off the current, we're starting to build up this charge on these various different things that are in the subsurface, and that's what essentially we'll be measuring as we cross over these different areas. We'll be measuring these variations in the distribution of potential or the voltage at the surface. And that's the thing that you have to realize too, is that we're taking these measurements at the surface. And so we're going to start to infer what is going down on below us by sort of the next steps that I'm going to get into here. And so the other thing I mentioned earlier, the dipole. So there's the dipole, but the other thing that you'll hear about in an IP survey is N and A. You know, N equals 6, A equals 25, N equals 8, A equals 50, or whatever. And so N is going to be the number of these dipoles that we're going to measure, and A is going to be the dipole spacing. And we're looking at the left-hand side, and basically in the old days, all that was done was what we refer to as a pseudo section, and they're still done today, mostly for part of the QA/QC process. It's one good way of seeing good and bad data points that are collected. But in order to do an IP survey, we're going to create what we refer to as an array of dipoles. And in this case, you see I've got 1, 2, 3, 4, 5, 6, 7, 8. So there's my N equals 8. And for sake of argument, we're using the dipole spacing is 25 meters. And from the start of the survey, excuse me, this is a dipole setup, where we see that these red dots are actually where the data is going to plot from the survey. So we're going to inject current, and then we're going to have a receiver here, and it's going to read all of these 8 channels, either subsequently or simultaneously. I think it's usually subsequently, but if you measure the first voltage and the first current, where we're going to plot that is generally down 45 degrees from each. And you can see that we've collected one line of red dots into the subsurface. And generally, the rule of thumb for depth of penetration of an IP survey, and it varies a little bit depending on the array geometry, is roughly 1/3. And in some cases, that's 1/3 the length of the array. So this array is going to be 8 times 25. So it's an array length of 200 meters, and roughly we're going to be getting down 66 meters. And that's sort of a rough thing, depending on the type of geology that you're in, how much energy you can get in the ground, whether there's conductive overburden. This amount will generally vary in terms of how deep you can get. Some people say, well, chargeability is a little bit less than resistivity, but that's all sort of dependent on the geology type of thing. So I have for a long time stuck with this rule of thumb. Third the length of the array is generally where we're getting to in terms of penetration. And n, so for a pseudo section, which is how we're going to plot this, I said that n equals 8, but for the first one, we're going to call that n equals 1, and this first dot is going to be plotted at level n equals 1. So each of these represents a level. When we're finished with this data collection, we're going to have n equals 8 different levels. We won't have an actual depth. We'll have this approximation of depth of 66 meters, but we're just going to have n levels, and that's what a pseudo section is. So I'm going to move on. And so in this example, I use n equals 6 and a equals 50. So and these were sort of the standard receiver technologies in the 70s, where n equals 4, n equals 6, 80s where n equals 8, 90s n equals 10, and you know that even up until recently, someone had a 32 n equals 32. And so what's going to happen here is we're sensing down roughly 100 meters, and in this case, the target's at the bottom of where we're sensing, so it's almost kind of pointless, but for the sake of the how we're going to collect this data, I'm just going to show you. So what happens is we'll do a complete move up of the array, and that is basically how we're going to cover a line, a survey line. And we'll leave behind these, we'll collect all the data points there, and effectively we'll be trying to produce a section that goes down about 100 meters. In reality is, if you want to see something at 100 meters, you really should be collecting data well below it. So in the 150 to 200 meter range is where you should be trying to collect data if you're actually interested in seeing, variances and changes down at 100 meters. And that's the same for if you have targets at 250 meters or 300 meters, you're going to have to figure out a means to effectively image at that depth. So presenting the data, this is the pseudo section. So you can see I take all these points, and basically I'm just going to put the data in there. There's all my n levels, and I'll color it all up. And if in this example, this is on the right-hand side, we see a chargeability model has low chargeability with a high chargeability feature in it, and we ran a dipole survey over it, and that is what you would get, and that is what used to be interpreted for IP surveys. Typically people would stick to dipole surveys because they were symmetrical, and so when you cross something you would get these symmetrical features. If you used a pole dipole survey, things would get skewed, especially depending on which direction you were going at. So they were a little bit more complex to interpret, and people would tend to stick with the dipole survey. We're going to sort of step into, trying to get real depth out of these surveys now. So we're going to go from pseudo section to depth through what we refer to as the inversion process. And so if you take those data points from the previous slides, and the slide isn't meant to look that complicated, but the dots are just the pseudo section levels, and there they are, n equals 1 to 8. So we have n equals 1, 2, 3, 4, 5, and 8 are where the arrows are pointing to. After the inversion process is we're going to show the data only in this red, in the yellow box, and that'll be the section. We'll be showing it effectively. The array n equals 8 equals 50, so the array is 8 times 5 is 400 meters long, so we're looking down 133 meters roughly. You know, the inversion process will actually show the data probably below that, but you know, we'll probably be using it down to about 133 meters. And that just shows you sort of the difference. In the old days, the pseudo section often looked a little bit deeper than what it really was portraying. So I'll talk a little bit about inversion here, and that's sort of dealing with the data. Geology is mostly 3D, but for 2D surveys, we typically use 2D inversion on 2D data. And basically what the inversion process is going to do is effectively put that chargeability and resistivity in the correct place at the proper depth based on the input parameters given. And so they're going to be much more useful for looking at the results of an IP survey with regards to your geology. And so on the left, we see sort of a couple of pseudo sections, resistivity on the top, chargeability on the bottom. And on the right are the inverted sections. And those are what we would use to interpret and target on, because now we have the data plotted at real depths. The inversion process does make a bunch of assumptions, and and one of the assumptions that it makes is that whatever you're crossing with your line kind of goes on to infinity each way. And you know, it's math, so somebody had to create all this math in behind the inversion that you know ultimately makes some assumptions to come up with answers. And so if you look on the left here, the top is actually the model, the geology, if you will, and there's various resistivities associated with it from conductive materials and such. And we're going to do an IP survey on it, and we come up with the second slide down in between the two green arrows. That's the pseudo section. And, you know, you can sort of see that there's some features down here, but, you know, what is that? So now we're going to invert it. Well, depending on what kind of parameters you use to invert the data, the results from the inversion can be drastically different. And this is sort of the cautionary note on IP surveys is this step usually either involves someone who's done a lot of this before, worked in these different environments before, or well, and that's probably the most key thing, but is also prepared to try different things. If, for instance, you said to your geophysicist, listen, I want you to, you know, do this as fast as possible, just grind me out the results and get me an inversion. Well, all of these 6 diagrams in the lower left here all speak to this data set that was collected here, and they all speak equally well. And that's sort of the big sort of cautionary note about inversion. What are you dealing with, and who's doing it, and which is the best one? And the best one arguably is really closest to a geological approximation. But if you have no idea of what your rocks are going to respond to, you know, you haven't done that physical rock property stuff earlier, then the first one out could be could be the first pass at getting physical properties on your property. It could be your survey. The only issue there is if you drill the feature and don't hit anything, then you might be saying, oh, that didn't work and I'll never use IP again. And you know, that's gone on for years. So it's cautionary is the inversion process. It's important to find people who are skilled at that. It's not a simple task, and sorting through which is the best approximation is a step that takes time, and it's just a fact. On the right hand side, this is how we're going to use physical properties to enhance interpretations. So in the middle, vertical middle that is, we see the geological model. So the geological model is known. Somebody's either drilled there before and they've assigned resistivities and chargeabilities accordingly. So the top panel are resistivities and the bottom are chargeabilities. Then we're going to do a survey, and the survey results are on the left. Those are our inverted results from carrying out a survey on the information in the middle. So we call that an unconstrained inversion. But if you actually know your geology that well, then what we suggest and have suggested for many years is, again, if you have a good handle on these resistivities of your background rock and your ore type and that sort of thing, that you can give this information that you've collected to the math ahead of time. So now it has some constraints. It can't just go, okay, well, I know things go to infinity each side of the line. I'm just going to give you an answer and get one of these lower left answers, one of 6 or more. You're actually giving it this geological model and saying, you know what, I already know this. So the data should respond to this. And in fact, when you do the constraint inversion on that data that was collected, you get the model on the right. And you can see that there's a huge fit here. Things have fit quite well down below. The anomalies explained, the middle things explained, and then you start to see up above, well, there's actually more to this little thing here that I used to think was there that goes right up almost to the surface. And then over here, there's this big conductive feature right along the surface. Well, you know, and the check to that, this is the top feature is probably the crown pillar in an underground mine here that was left behind. And this purple thing on the surface turned out to be a tailings pond that was, you know, subsequently covered over with grass and dirt and that sort of thing. But at least it's explained. And so this is a way that you can use it, or use the data, use your geology more effectively, and squeeze more out of your geophysical surveys. Having done or been involved in a lot of these projects in the past, these types of projects, it's time consuming, and it's, you know, it takes dedicated people thinking about it. Okay, I see I'm gonna have to go through about 40 slides in 1 minute here. No, I'm just kidding. But I do have quite a few slides to go. I'll try and speed it up a bit. By increasing the number of dipoles and also increasing the dipole spacing, deeper investigations can be achieved. I guess I'm supposed to press the button here. And so there's our survey that we showed you earlier. And one way of getting deeper is by adding more dipoles. So instead of n equals 6, I go n equals 8, 9, 10, and that helps drive out more depth. The other way I can get more depth is stretch out those dipoles and make big, wide A spacings, and that gives me more depth. So we're going to get deeper that way. And one of the problems with doing that is all these wires on the surface. That turned out to be a real Achilles tendon in getting deep data. A lot of crosstalk between the wires, what we refer to as EM coupling, et cetera, et cetera. And this was a large problem. Although back in the early 90s, Quantec was fortunate enough to be involved in a couple of discovery type projects down in South America. And this is the kind of data we were collecting. Instead of doing the 25-meter dipoles that you see in the top left of this section, we spread things out and we were collecting big, wide surveys. And, you know, with a lot of effort on the top, on the surface, getting a current into the ground, you know, several significant deposits were identified. And this is, you know, a porphyry type environments. So how did we get deeper? Well, that was that advent of DAS technology. And it always sounded confusing to me at the beginning, distributed acquisition system technology. Wow, you know, what does that mean? Well, basically, all we were going to do is, instead of having one computer that measured 6 or 8 or 10 or 32 things with lots of wires and such, we were going to have a computer that just measured like 2 things. And what we were going to do was put a lot of computers out, and they would just keep measuring these 2 things, or in some cases 3 things. And as we got more advanced, there's, you know, 6 things. But the big thing was that we could stretch out our arrays almost infinitesimally in terms of length. And it really became, well, how much can you get done in a day? And practically speaking, we could get our arrays set up to be, you know, 2,000 meters, oftentimes 2,400 or 3,000 meters. And now you can sort of see that we're starting to, if you put out a 2,000 meter long array, we're starting to get down into that 700 meter, well, 2,400 meter array is going to give us that 750 depth penetration. So very useful for imaging anything from 2 to 600 meters, say. And that sort of was the, you know, the big story of Titan. Titan is was the first commercially available distributed system. And this is a picture of a Titan 24 setup. In the old days, we were pretty well, it was a standard length was 2,400, but it, you know, didn't have to be. The dipoles could vary in size, anywhere from 25 to 400 meters if you wanted them. And we would set up the whole array ahead of time. So that whole thing would be set up, and that way when we put the current in the ground for a pole dipole survey, we would have one current off at infinity, one here on the left. We would measure at all these dipoles simultaneously, 24 of them. And then we would move up and measure again, move up, measure again, move up, till the end of the day, we would be at the other end, and we'd still be collecting data behind us all the way back to the back. So it was very novel in terms of the volume of data that we were collecting. I show some magnetometers here on site. That's because these computers could be multitasked. So once we finished with an IP survey during the daytime, we would just let that thing sit there and we would collect MT at night. And that in itself was pretty novel at the time. And we've expanded on that. And there's, I don't talk about it in this presentation, but so again, we're collecting 2 sets of data with this DAS system. So we have transmit behind, collecting all the receivers in front. By the time we're at the end of the survey, we've collected all the receivers behind. We actually combine both of those big data sets to be one big triangle of data, and then we drive out the inversion from that. And then, well, there's a point, you know, what about this triangle of data? That's the pseudo section. There isn't a lot of data over here underneath the ends of the lines, but the inversion, the way it's set up, typically will put out a square or a rectangle of data. So for us, it was not best solution set. So very early on, we figured out that, well, if we just keep going beyond the end of the, if you look at the upper right here, these blue arrows are where we're going to just carry on beyond the end of the survey and just add in more current injections. All these dipoles are going to be sitting there measuring away, and we'll collect data for under the ends of the lines. And this is something that is very useful tool depending on your concern for collecting data right up to the ends of your lines. There's a whole bunch of neat little things in behind these DAS systems. I mentioned, current monitor. Well, one of the things when you're injecting current with a survey line and you move through a swamp, you're getting a lot of current into the ground in the swamp. Then you come out of the swamp and you're up on the barren outcrop. You're not getting as much current into the ground. And most traditional technology wouldn't account for that. And so it was essential that you actually monitored. You couldn't just say you're always getting 4 amps into the ground. Sometimes you're only getting 0.1 amp into the ground. And so it was important when you went to make your calculation that you knew what the current was going into the ground. And then other small things, instead of the duty cycle on the Titan in particular DAS system was 100%. So instead of going on and off and then off negative, we would just go from on positive to on negative, and that was our current waveform. And you can see the difference between these curves here that you're looking at is that decaying IP chargeability effect. The top one is 50% duty cycle, the bottom was 100. So it was just a means of constantly trying to achieve a better number out of the ground. And this technology helped do that. And there was a bunch of other sort of nuances in the system. At the end of the day, it was like a huge benefit for, making decisions. So more reliable targets once you were below 150 meters, and you could make better decisions on where you're going to drill. In the past, pretty well, this is what you were left with. You get a 100-meter data set, and you're drilling down at 250 meters, 300 meters. It's like, okay, could be a lot of conjecture. This bottom section here would help you make some decisions faster, whether or not these are the mines or not in your property. I'm getting close now, but just this is, I put this in here, found this the other day actually, and I just thought I'd show it. This shows the impact of a couple different survey geometries. And one of the things you can do is you can investigate your ground or how an IP survey would respond on your ground with forward modeling. So if you have your geology well known down below in the lower left, you have a concept of what you have or what you think you have, and you've gone to the trouble of figuring out what your resistivities and chargeabilities might be in the subsurface, you can actually give this model to geophysicists in general, and they can do some forward modeling. So they might simplify things, of course, to deal with that geological model, and that's what we see on the top left. So that's the simplified physical property model of the geology. And now we can pretend to do some geophysical surveys over that. And so what we're going to do is an IP survey, and we're going to show resistivity. And we're going to do it with dipole. And that's what you get on the top left. Pole dipole, that's the middle, and pole. And the pole, of course, is putting this huge amount of field in the ground. And so you got the depth, but the resolution isn't quite as good as the middle one. And then, of course, the dipole's not too bad, but it's truncated at depth. And depending on your objectives, that's all a factor too. In this case, we actually had the opportunity to actually go and do the real survey after the fact. So we had that model assumption before, and then we did the survey, and it was quite phenomenal. My colleague at the time, Jean Legault, and others put this study out in the Leading Edge in the late 2010s. What is that? Late 2000s? Anyhow, and I just happened to find it the other day, so I thought I'd add that in. And that was sort of the segue into forward modeling. You know, trying to convince somebody to do a survey, sometimes it's like, well, I didn't have success before, but you know, if you have, again, this is a great case study for us, was Kemess. Spend a lot of time convincing them that they should maybe try out the technology. And so we went to great lengths to get resistivities and modeled up what they thought. So this was their wish, that they had the Kemess porphyry, and that things had been, you know, faulted off, and it's down here, and it's over along this boundary. And so what would you get if you ran a big Titan line over the top of this for an IP survey? And so, you know, we did the forward model, and this was the raw data of a big long line, 5 kilometers long, and we had to do it in looks like two spreads with an overlapping spread. And these were the results. And they said, wow, so if my dream is there, you guys can see it. And it was really exciting times for us, because we did this line over the mountains, and there you see it. And these were the results. And in fact, this was their new discovery down in the middle here, which those guys won the Prospector of the Year award for. And I'm not bitter. But in the end, the survey helped the team when I discussed it with them. You know, of course, the discovery wasn't the blob. And this is sort of goes to my point earlier about understanding your geology. The discovery, as I was pointed out, I said, geez, you know, we gave you a big blob under the mountain. He goes, well, Rob, the blob wasn't the discovery. The discovery was right below the blob. And I said, oh, well, okay. And so, you know, that was where we helped them vector directly to discovery. And then another very big success was at Copper Mountain, where we went over some old pits, and the blue dashed line was the pits that they were planning. We did the survey, big long IP line, big huge chargeable blob underneath the pits they drilled, and basically they changed their design of their mine based on the data that came out of these surveys. And in the process, this image helped them raise $50 million. It was so significant. They were using this in all their please give us money presentations. So that was a big success. So, you know, Titan continued to advance, and we're now deploying what we refer to as Titan 130, Titan 160, and we sort of dropped the 24 moniker, and we kind of just refer to it as Titan. It can be 24, 130, 160, doesn't really matter. It's based on the same sort of principle in our experience. But in this example, we were able to lay out 7 kilometers of dipoles. And we collected simultaneously, ran through it with the current, just like the Titan. We're able to collect these massive sections of DC resistivity and chargeability. And what's of point here is that note that we're not planning to show at the end of the day, resistivity and chargeability, you know, we're putting current in the ground, it runs out of steam. It just doesn't get down forever. So that 1/3 rule of thumb that I mentioned earlier stops to be effective. And in this case, so we're not showing 2 kilometer sections. And the inversion actually tells us when we're doing it. There's a sensitivity analysis that goes on, and we apply certain cutoffs, and that all speaks to who's grinding through your data and is making the right decisions about, in fact, what we are seeing. And so that goes for resistivity and chargeability. The cutoffs are different, and then ultimately we'll come up with a product that we feel comfortable presenting. I see I've gone over just a little bit here, but I'm just on my last couple slides here. And so basically, critical components of an IP survey, proper data collection. You're going to come up with an array geometry. You can either trust your provider or they'll provide you with a solution set, perhaps. It's important that all the right things are being done in the background, and those are questions that maybe you'll just think to ask yourself. If you've got a dry, rocky environment, you might ask them how you getting that current in the ground, those sorts of things. So proper data collection is a big, huge thing. The next thing is, once you've got that data, is the reliable processing and inversion that goes on behind the scenes, in like who's doing that. Is it just one guy, or is it a team of people who've done thousands of surveys before? So that's a factor. And then just in closing, we talked about 2D geophysics, and typically lines are set up to cross the strike because it's meant to provide best coupling with perpendicular features. The inversion process, the math is kind of geared to things that go on infinity in a 2D direction. But as you guys all know, geology is more often than not 3D. So complex geology and structure can't really be captured by one 2D approach. So in this case, on the left, you see a bunch of lines here. They're meant to show you lines that are crossing various strikes, and there's your property. So oftentimes, in the old days, there would be grids that went this way and grids that went that way, because geophysicists were trying to accommodate that. And that's sort of what we get into in the next presentation, IP 102, which is advances in real 3D data acquisition. And there's been a lot of improvements in the last 20 years in IP surveying. I'll turn it back to Christian. He can yell at me later for going over, and there are our contacts.
Great, awesome. Thank you very much, Rob, for the presentation. We are grateful for the time and effort you took to share your thoughts and experiences with this big group of explorers. Today we had more than 100 attendees, so pretty good. I believe we can all benefit from the topic discussed today. Now I would like to open the floor or the session for questions or comments. I'll open